Welcome to the Explainer. Today we are going to go on a pretty wild ride. We're starting with something you might have collecting dust in your basement and ending up at the very edge of modern mathematics.
Yeah, I know. It sounds like the setup to a really nerdy joke, right? You've got this physical thing, a compact disc, that stores music with tiny little pits and bumps. And then you have abstract algebra, one of the most theoretical, out-there fields in all of math. But I promise you, there is a deep, truly beautiful connection between them. And today, we're going to find it.
All right, so where do we even begin? Well, our first clue isn't hidden in some complex formula. It's actually right there in the data itself. See, for that CD to work at all, the data has to play by a very specific, secret set of rules.
Now, what's so cool about this is that it's not some arbitrary math rule. It's a physical necessity. The laser that reads the disk needs this kind of pattern to stay on track and not get lost. It's a type of rule called a run-length limited constraint. The main idea is super simple. Some patterns are okay, and other patterns are forbidden.
And it turns out there's a whole field of mathematics dedicated to studying exactly these kinds of systems. It's called symbolic dynamics. It basically gives us a formal language to talk about any system, from data storage to biology, that can be boiled down to a sequence of symbols that has to follow a rulebook.
Now, to keep things from getting too crazy, we can zoom in on a special kind of system. It's called a shift of finite type. All that means is that our listed forbidden words is finite and not infinitely long. And maybe the simplest example of this is the rule no consecutive ones. That's it. The entire list of forbidden things has just one entry, the word 1-1. It seems almost too simple, but trust me, this is the key that's going to unlock everything.
So, okay, we have these rules, but a list of what you can't do is kind of hard to work with. The next big idea is to make these rules visual, to literally turn them into a picture.
And this is just a brilliant leap in thinking. Instead of a boring list of forbidden words, we can draw a map, a directed graph, with dots and arrows, can perfectly capture our set of rules. It basically acts like a machine that can generate every single possible sequence that's allowed.
Let's take our super simple no consecutive ones rule. The graph is easy. We've got two locations, or vertices, let's call them 0 and 1. Now we just draw arrows for the allowed moves. From a 0 you can go to another 0 or to a 1, and from a 1 you can go to a 0. But, and this is the crucial part, there's no arrow going from 1 back to itself. Why? Because that would create our forbidden word 1-1. The rule is baked right into the drawing.
And this is what makes the graph so incredibly powerful. Any path you can trace by following the arrows spells out a perfectly valid message. And any message that breaks the rule, well, you just can't draw it on this map. There's no path for it. The graph is the complete rulebook.
Okay, so this is an amazing visual tool, right? It's a complete map of our system's language. But can we push it further? Can we actually take this simple drawing of dots and arrows and turn it into a real, rigorous, powerful algebraic system?
The answer, amazingly, is yes. This is where we take that leap, from a simple picture to a whole new kind of algebra.
It turns out there's this kind of universal recipe, a method that lets you take any directed graph you can imagine, no matter how simple or how ridiculously complex, and build an algebraic structure directly from its pieces. The dots, the arrows, how they're all connected, it all gets translated perfectly into the language of algebra.
And this table here really breaks down the translation. It's a one-to-one mapping. A vertex, or a dot on our graph, becomes something called a projector in the algebra. You can think of it as an element that says we are currently at this location. An edge or an arrow becomes a generator. It represents the action of moving from one location to another. So a path along the graph, it just becomes a word in our algebra, a sequence of these moves.
And this amazing structure has a name. It's called a Leavitt Path Algebra, or LPA for short. The real beauty here is that the algebra doesn't just describe the graph. In a very real way, the algebra is the graph. Every single property, every rule of the algebra comes directly from the shape and connections of that original drawing.
So you might be thinking, okay, that's a really clever trick. But this connection, this bridge between simple graphs and complex algebra, it turns out to be something so much bigger.
This algebra of paths is really like a Rosetta Stone for modern mathematics. It creates a shared language. It allows us to connect and translate between fields that, on the surface, look like they have absolutely nothing in common.
And the sheer scope of this connection is just staggering. This exact same algebraic idea, the Leavitt Path Algebra, it just keeps popping up everywhere. It describes symbolic dynamics, the rules of data we started with. But then, it also provides a foundation for C-star algebras, which is the math behind quantum mechanics. It helps us understand K-theory, which studies the shape of abstract spaces. It is this incredible unifying thread that runs through huge, distinct areas of mathematics.
So we've really come full circle. We started with a very down-to-earth problem. How do you reliably store Beethoven's Ninth Symphony on a little piece of plastic? And by just following that one single thread, we've uncovered this deep, hidden algebraic structure that reveals these profound links at the very heart of mathematics.
It really makes you wonder, doesn't it? If this elegant, powerful mathematical structure is secretly hiding inside something as ordinary as a CD, where else might we find these invisible algebras? What other parts of our world are being quietly governed by the beautiful, abstract rules of some hidden mathematical language?